Yeah, I'm talking about Mistral and Tramontan in CORDEX simulations. And so first I'll explain what Mistral and Tramontan are. So Mistral is a wind channel in the Rhone Valley here, going on the Mediterranean Sea, and Tramontan is following this valley, and they both can cause deep water generation and therefore are important for the modeling of the Mediterranean Sea circulation. And the first question was on which days we have a Mistral or Tramontan event, and we got the station data from 16 stations, 13 stations from Météo France, and they contained the information if there was a gust from the Mistral or Tramontan direction at these stations of above 60 meters per second. And we then decided to regard the day as a Mistral day if these gusts were observed up in the valley, where the valley opens to the sea and close to the shore, and similarly for Tramontan. And for the 30 years, 1981 to 2010, we arrived with about 1,400 Mistral and Tramontan days and about 7,000 days where none of the winds occurred. Okay, and then one of the questions we wanted to answer was how well the RCM simulate the patterns of Mistral and Tramontan wind speed and wind direction when they have the chance to actually model the channeling in the valleys. So we wanted to know when the large-scale pressure patterns are simulated well. And we had a look at 5 RCMs from different groups and on 50-kilometer resolution and smaller grid spacing as well. And I show biases compared to QuickSCAT data over the sea and Saffron data over France. To find out if this large scale was simulated well, we used the Bayesian network, and we did an UF analysis of area interim sea level pressure fields and fed the principal components and the observed time series into this Bayesian network. And after training, we now can put the, training of the Bayesian network, we can now put in the principal components of the RCMs, which were projected on the area interim EOFs, in the network, and it gives us a number. And the higher the number, the more likely there was a Mistral or Tramontan event. We then transformed this output into a true-false variable by just keeping the number of Mistral and Tramontan events the same as in the observed time series. And then we arrive to about 74 to 82% of the cases being correctly identified by the models. Now, these are the biases of the RCM. So each column belongs to one RCM. And the upper row is the coarse resolution, and the lower row the finer resolution. And here's error interim. Only at Mistral and Tramontan days where the Bayesian network told us that the sea level pressure pattern was represented well for each model. And we now see that even if the models overestimate the wind speed over land, they all show an underestimation over the Mediterranean Sea, especially at the borders. So the main flow goes here, and actually this one shows a little overestimation at some points, but in general they underestimate the wind speed. And we did the same for wind direction. Here we only had data from QuickSCAT, and so red means a clockwise rotated bias. So in this case, the wind speed comes too far from the right, let's say. And again, the models show a similar bias, and blue means counterclockwise, of course. And the bias here is stronger at the borders of the flow again, especially in this area. The one thing which varies between the models is the parameterization of the sea surface roughness length set 0, which is most of the times formulated in the Januk formula, relating a constant parameter times the friction velocity. And because the model I showed before, the one overestimated the wind speed a little, and this was our calculation. We did the same calculations with higher values for alpha, which showed a decrease in wind speed, but also a counterclockwise rotation of the wind direction, which fits well to our clockwise rotated bias, but unfortunately we get an underestimation or even stronger underestimation of the wind speed at the same time. This calculation were done by one of our master students, Ben. And the second big questions we had was, do the characteristics of Mistral and Tramontane events change in climate projections? So first we again had a look at the era interim period. But now for CCLM, ALADA and REXCM. And we used the same Bayesian network. And here I plotted the Mistral days per year and the Tramontane days per year for 1980 to 2010. And the black line is the observation and the color lines are the models. And so we see that if we have error interim forcing, the models get the number of Mistral days and Tramontane days per year quite well. So, but they all overestimate the period length. So period length is how many days in a row a Mistral or Tramontane occurred on average in this case. And we have 1.7 days for Mistral and 2.5 for Tramontane, and so these numbers they all are higher. And the seasonal distribution also is reproduced in the models, but I did not show this here. So now we come to the historical and projection runs. We basically did the same as before, and we now made sure that in the period for which we have the observations, so 1980 to 2010 or wherever the historical run ends, we have the same number of Mistral and Tramontane as in the observations. So this causes some changes here. And so we see that most of the models show similar numbers of Mistral and Tramontane days, except one. And we also already see that, so the dashed lines are the historical, the full lines are the RCP 4.5, and the dotted are RCP 8.5. We see that the 8.5 in the late 21st century lies below the 4.5. And I also plotted the period length, and all of these are 10-year running means. And we have now MPI ESM-driven runs and CMCC CM-driven and one head GM and CM5. So 4 different GCM-driven simulations. And so we can see how the mean number of days changes on this slide. So here are the models again, and the first row always is historical, then 8.5 and 4.5. And the columns are the mean number of Mistral days per year and Tramontane days per year, and for 4 30-year periods. And the numbers I wrote here in red are higher than those 1981 to 2010, and the black ones here are lower than here. And the bold numbers pass the 95% significance test of difference in means. So we can see that most models agree on less numbers of Tramontane days in the 21st century, but for Mistral it's a little different. So some show increase and some show decrease, but all models show that the numbers in the 4.5 run are higher than the numbers in the 8.5 run. So we expect less Mistral and Tramontane days in 8.5 than 4.5. Okay. And so now we're wondering how the Bayesian network found these. And as I told you, we did this EOF analysis. Here I showed the first 5 EOFs of the error interim. and also a correlation between error interim and the Mistral and Tramontan observations. And we see that the first two principal components correlate with Mistral and Tramontan, while the third anti-correlates. And if we have a look at the trend in the principal components for the different runs, we see that we have a positive trend in the first and in the third, and a negative trend in the fifth principal component. And the fifth principal component correlates with Tramontan, so we can see why the Bayesian network tells us that we have less events in the future. And then I also plotted the wind speed. Also, these are 10-year moving averages in the Mistral and Tramontan area in the 90th percentile. And the upper part of the plots is the Mistral days, and the lower part is the non-Mistral days, and the same for Tramontan. So you can see that the wind speeds during Mistral and Tramontan still are way higher than those on the non-windy days found by the Bayesian network. So we still expected to identify the days with the high wind speeds. And then I already arrived at the conclusion. So we saw that the RCMs underestimate the wind speed, but they get the days per year well, even in the historical, and the overestimation of the period length occurs in all models, and we don't see a significant change in Mistral days per year. The models are not sure if they show an increase or decrease, and but the Tramontan days per year decrease, and the changes are stronger in the 4.5 in the 8.5 run than in the 4.5 run. Thank you.
Thank you very much, Anika. There's a question, please, Philip.
Basically, Tramontan and Mistral are, say, companion winds, so it's the passage of the front that is distorted by the mountain. And so, how would you explain such a non-significant trend in Mistral days versus apparently significant days trends in T days? And do you relate that to the storm track position or evolution of the storm track position?
Yeah, so I, at the moment, cannot really explain why the Tramontan changes differently, and even in some of the models, the Tramontan changes, so decreases while the Mistral increases, so in those models. But we already saw that these principal components show different correlations with the Mistral and Tramontan events, so maybe it's something, as I said, that the pattern somehow changes differently, and they are not completely connected, only partially. I don't know.
Yeah, thank you very much.